Okay, you can also use intermolecular forces to explain solubility. When two substances interact, the interaction depends on how well do they like to stay among their own kind, so attractions among like molecules, and how strongly they would like to mingle with the other types of molecules. So interactions between unlike molecules versus interactions between like molecules. So in terms of solubility, for you to be if you want to explain why does something dissolve in water and why does something else not dissolve in water, that you can explain that using the rule of thumb that's known as like dissolves like. So if you have a molecule that's very similar to water, they can interact with water the way water would interact with other water molecules, you would expect it to be soluble in water. Okay? But if they're not able to interact strongly with water molecules, so the structure is very different, then more likely it's going to be insoluble in water. Okay? So since water molecules are polar, okay, substances that are made up of small polar molecules will tend to be soluble in water than they would be in a nonpolar solvent. Similarly, if you have nonpolar solvents, if you have polar solutes, your solute molecules will tend to stay amongst themselves rather than interact and mingle with those nonpolar molecules of the solvent. So like dissolves like. So how do you explain why ethyl alcohol is soluble in water but vegetable oil is not? Ethyl alcohol, this is the structure of ethyl alcohol. Can you see how that's very similar to water molecules? They're capable of hydrogen bonding interactions with water molecules. So they can blend in, you might say, among the water molecules. Okay? So they can mingle easily with water molecules. What about vegetable oil? Now, the structure must be very different. Vegetable oils are very long chains of carbon and hydrogen atoms. Okay? Carbon atoms is a hydrocarbon with a COOH at the end. Okay? So this very long part of your molecule, so this will be an example of fatty acid. Okay? Each corner here you have a carbon atom and then you have hydrogen atoms attached to those carbon atoms. So this carbon has 2 hydrogens. This carbon has 3 hydrogens. So each one of these corners has a carbon atom with hydrogens attached to it. Okay, so this is a very long, you might call a hydrophobic part of the molecule. So you might call that a hydrophobic tail of the molecule, which will not interact well with water molecules because these are mostly nonpolar bonds, right? So that's the explanation why oil and water don't mix, because it has to do with the structure of the molecules. Okay, they're very dissimilar, very different. Now, this part of your fatty acids can interact with water molecules. So it's what you would call the hydrophilic part of the molecule. Why is it hydrophilic? Phil means, okay, hydrophilic means water-loving, right? Like Philadelphia, city of brotherly love. Phil means love. Okay? So if you have this thing right here, so this part of your molecule would be attracted to water molecules. How? How will this part of the molecule be attracted to water molecules? You can have hydrogen bonding interaction, right? Okay. And phobia, water fearing, right? That part of the molecule will stay away from the water molecules. All right. So here's stearic acid. It's a fatty acid. Is this likely to be soluble or insoluble in water? You have a very huge hydrophobic part, a very huge nonpolar part, so you would expect this to be insoluble in water. Okay. Which of the following is least soluble in water? NH3, HF, or CH4? How would you determine this? NH3 and then HF and you have CH4. All right. So which one is least soluble in water? Okay, very good. Why? This is nonpolar, right? Not capable of hydrogen bonding interactions. Whereas this fluorine right here, that lone pair can be attracted to water molecules by hydrogen bonding, and that hydrogen can be attracted to a water molecule also by hydrogen bonding, right? Same thing with the NH3, and this is also polar, okay? NH3 is also polar, and it's capable of hydrogen bonding interaction with a water molecule. Okay, so I have a water molecule here that can interact with that hydrogen because this hydrogen is attached to a nitrogen. Anytime you have hydrogen attached to fluorine, oxygen, or nitrogen, it's easy to remember. Phone, okay? Fluorine, oxygen, or nitrogen, the three most electronegative atoms, then that hydrogen is capable of hydrogen bonding interaction with a neighboring molecule that has oxygen, nitrogen, and fluorine with a lone pair. Okay, so water, for example.